Okay, so in this section, section 4.6, I want to talk about exponential and logarithmic models. So basically applications of using exponential and log functions. So 4.6 is on exponential and logarithmic models. And the first thing I want to talk about is something called radioactive decay. Okay, so what is radioactive decay? Well, it has to deal with the half-life of a substance that undergoes radioactive decay. So the half-life of a radioactive isotope is the time it takes for half the substance to decay. So is the time it takes for half the substance to decay. Okay, so actually let's derive an equation so that we can solve for the half-life. So if I start with my general exponential growth decay equation, so let's say I'll do it this way, given the basic exponential growth decay equation, which we know as f. I'll use t as my independent variable, right, my input, because we're dealing with time. So it's f of t equals, remember, just a times b to the t. So half-life can be found by setting f of t equal to half of a, right? Because remember, a is the initial amount, right? When t is 0, b to the 0 is 1. So a is the initial starting amount that you have of that substance. So if we want to find the half-life, we want to find the time when the output, f of t, is equal to half of the original amount. So if we set f of t equal to a half of a, right, that would be half the original amount, and solve for t, that should give us the half-life. Okay, so let's do that. So I will have, on the left-hand side, I'll have a half of a is equal to a, b to the t. Now, of course, we can cancel a's, right? You can divide both sides by a, so the a's are gone. And then I have b of t equals 1/2. But then how do I solve this equation for t? It's just an exponential equation. Remember, we take the log of both sides. And you can use any log you want. I'm going to stick with natural log. So I would do natural log of b of t is equal to natural log of 1/2. But remember the rule, right? The exponential property of logs is that t will come out front. And then finally, I can divide both sides to solve for t. I can divide both sides by natural log of b. Oops, so this is going to be ln of b, ln of b, right? So this will cancel, and that is my equation for the half-life. So I'll write it here. T is going to be equal to, it's just going to be natural log of 1/2 divided by natural log of b. So it really just depends on b, right? If we know b, then we can plug into that equation, and that will give us the half-life. So this time right here is the half-life. Okay, so here's an example. Okay, so here's an example. A scientist begins with 250 grams of a radioactive substance. After 225 minutes, the sample has decayed to 32 grams. We want to find the half-life of the substance. Okay, so start with the general exponential growth decay function. In this case, it'd be decay, right? So we have f of x is equal to a b to the t. Now, what we'd like to do is figure out what b is, because then we can plug b into the half-life equation, and that will give us the half-life, right? So how do we find b? Well, what information are we given here? A scientist begins with 250 grams, right? That means when time is 0, you have 250 grams. So that means a, right, must be equal to 250, right, grams. After 225 minutes, the sample has decayed to 32. So in this case, t is going to be equal to 225 minutes, right? Units are minutes. And then the sample has decayed to 32 grams. So that means f of t, actually, I should really write this. I wrote an x here, but I really should write that as a t, right? So let me change that, write this as a t. So that means f of 225 must equal 32, right? My output must be 32 when the time is 225. So I can just plug this in. So on the left-hand side, this is just 32. That's equal to a, which we know is 250. And then it's going to be b to the 225. Okay, so let's solve this for b. How do I do that? Well, first, let me isolate the b to the 225th power. Let me isolate that term first. So how do I do that? I need to divide by 250. Divide by 250. So I'm going to write this on this cancels. I'm going to write this right-hand side on the left-hand side. Doesn't matter, but just so it's cleaner that way. And then 32 over 250. I could simplify that. I'll just leave it as 32 over 250. Okay, but you could simplify that, right? It looks like 2 definitely goes in, maybe 4 as well. I guess 4 doesn't go in, but 2 definitely goes into both of those. Okay, how do I solve for b now? I have b raised to the 225th power, and I want to undo that. So what you would do is actually you would take the 225th root of b to the 225, and whatever I do to one side, I have to do to the other side. So that'll give you b, right, on the left-hand side. Well, how do you do that on your calculator? How do you do the 225th root? Remember, you would take your number, so this fraction, and you would raise it, so use the caret, and raise it to the 1 over 225th power. And that's the same thing as the 225th root. When you do that, you're going to get around it should be a little less than 1, right, because it's decaying, and it's 0.99 is what I got, rounded to 4 places. Okay, so now that we have B, now we can find the half-life. Remember, the half-life, the time for half of the substance to decay, is going to be the natural log of 1/2 divided by the natural log of B, but B we know is 0.9909. We knew it had to be less than 1, and it's only slightly less than 1 because it's decaying, but it takes a long time to decay. Okay, so if I plug this into my calculator, I'm going to get around 75.8 minutes. So that would be the half-life of that substance, around 75.8 minutes. Okay, here's another example. Okay, so this question says, a wooden artifact from an archaeological dig contains 60% of the carbon-14 that is present in living trees. How long ago was the artifact made? And we're also told that the half-life of carbon-14 is 5,730 years. Okay, so the goal is to figure out how long ago the artifact was made, given that there would be 100%, right, of the carbon-14. And now there's only 60%, and we know that half-life time. Okay, so how do we start this problem? Well, let's start with the fact that we know in general, right, that we have, our exponential decay equation is going to be f of t equals ab to the t. And we're given the half-life, right? So actually that should allow us to find b, because, so remember, the half-life is when f of t is equal to half of a. So that's going to equal a, b, and we're given the fact that the half-life is 5,730 years, right? 5,730 years. So t in this case is 5,730. Now the a's will cancel. And then if you work this out, let me just move this term to the left-hand side. We're used to seeing the variable on the left-hand side. Doesn't matter, but just easier that way. And then how do I find b? Well, I need to take the 5,730th root, right, of both sides. But that's equivalent, so this is 5,730, but that's equivalent to raising 1/2 to the 1 over 5,730 power, right? And that turns out it's around, and you have to go to several decimal places to get an accurate, because it's very close to 1. It ends up being 0.999879. Okay, so that's B. So now let me go, now that we have B, right, I'm going to plug back into my general equation. So I have f of t is equal to a, and now I know b is 0.999879 to the time t. And I want to know the time, right? I want to find the time. Let me write this out here. We want to find the time t when f of t, the output, is equal to 60%. So it's equal to 60% of a. But how do we write 60% of a? We could just write that as 0.60 a. Right? So if I plug that back in now, or have f of t, if I put in 0.60 a, That's equal to a times 0.999879 raised to the t. And now look what happens. The original starting amount doesn't matter, right? Because it cancels. The a's cancel again. So the a's cancel. And then how would I find t? Well, I would take the log of both sides, right? So I'll take the natural log of the left-hand side and then the natural log of the right-hand side. Then I can use the exponential property that t will come out front, right? That's one of the properties of logs. So I'm just going to write now that right-hand side on the left-hand side, just to reverse it so I can put my variable on the left-hand side. So this is going to be t times natural log of 0.999879 is equal to natural log of 0.60. And now I can divide both sides by natural log of 0.999879, right? And that will allow me to find t. So these will cancel. Whatever I do to one side, do the other side, so I'll divide on the other side. And then to get the final answer, you have to plug that into your calculator. So if you do natural log of 0.6 over natural log of 0.999879, you're going to get around 4,221.4 years. So that's the age of the artifact. And actually, it makes sense that it's a little less than 5,730, right? 5,730, because 60% of the original carbon-14 was remaining. And remember, the half-life was 5,730 years, and that would be the case if only 50% of the original carbon-14 was remaining. But we have a little more, 60%, so it's not quite as long. So that makes sense. So it seems like a reasonable answer, and that is the correct answer in this case. Okay, so that was half-life. The next thing I want to talk about is sort of like the opposite. It's the doubling time. Like, how long does it take something to double? So doubling time the doubling time of a growing quantity is the time it takes for the quantity to double. So again, if we start with our general exponential growth and decay equation, in this case it's going to be growth, right? F of t equals a b to the t. By the way, the only difference between growth and decay is the b, right? If the b is larger than 1, it'll be growth. If the b is less than 1, and notice how in the other examples it was close to 1, but it was always less than 1, that was decay. Okay, so in this case, we want to know the time, so we want to figure out t, when the output f of t becomes twice the original amount a, right? So if I plug in 2a for f of t, that's got to equal a b to the t. Now the a's will cancel, right? These cancel. So now I have, I'll write it the other way again, b of t is equal to 2. I'll take the log of both sides. I'll use my property that the t will come out front, right, the exponential property. And then finally, to get t by itself, I'll divide both sides by natural log of b. So that's going to be the doubling time. So t is equal to natural log of 2 over natural log of b. Remember, the half-life was natural log of a half over natural log of b. The doubling time is natural log of 2 over natural log of b. So in this case, this t represents the doubling time. So this is the doubling time. Okay, so here's an example. Okay, so in this question, we're told the count of bacteria in a culture was 800, so 800 bacterium in a culture after 10 minutes, and 1800 after 40 minutes. And we want to answer, given that initial information, we want to answer several questions. What was the initial size of the culture? Find the doubling time, find the population after 105 minutes, and when will the population reach 11,000? Okay, and we're assuming that the bacteria are growing exponentially, right? Okay, so let's start with our general exponential growth equation. Right? In this case, it's definitely growing, not decaying. So remember, it's f of t is equal to a times b to the t. And in this example, we're given some initial information, right? We're given the bacteria count at a particular time, and we're given two pieces of information, right? We're given there's 800 bacteria after 10 minutes and 1800 after 40 minutes. So actually, I could plug those values into the this equation, and that will give me two equations, and I'll have two unknowns, just a and b. So this will allow me to find a and b. And once I have a and b, I have my general, or actually in this case, it'll be my specific exponential growth equation, and then I can answer any question, right? If I have a and b, I know exactly what the equation is for this particular problem, and I can answer any question about the problem. Okay, so let's do that. Let's find a and b. Well, I know if that f of t is 800, don't know a, don't know b, the time was 10 minutes, right? So I'll just do t is 10. And then the other possibility is when the count was 1800, the time was 40 minutes, right? So t is 40. So time is going to be in minutes in this particular problem. Okay, great. So there I have two equations, two unknowns, right? A and b. How do I solve these? Well, I could use substitution. I think it's easier just to divide them, though. So let me write these out again. I'm going to write this one. First of all, I'm going to put the variables on the left-hand side, just because it's easier. We're used to seeing the variable on the left-hand side, but it really doesn't matter. So this is equal to 1800. And then what I'm going to do is I'm going to divide by the first equation. A, b to the 10 is equal to 800. Why am I doing that? Because I recognize if I divide those two equations, the a's are going to cancel, and it'll allow me to find b, right? Then I can go back later and figure out what a is. So if I divide, a's are gone, because a divided by a is 1. And then what's b to the 40th divided by b to the 10th? Well, remember the rule is that you would subtract the exponent. So this is b to the 40 minus 10, which is 30. And that's got to equal 1800 divided by 800, which actually in this case, I guess 200 goes into both of them. So we can simplify this to 9/4. Or you could write it as a decimal if you want as well. And then how do we find b? Well, now if we take the 30th root, which we know now that that's just the same thing as raising it to the 1 over 30, right? The power 1 over 30. By the way, you can see this, right? Remember, if I raise a power to a power on the left-hand side, if I raise b to the 30th to 1 over 30, I multiply the exponents. And what's 30 times 1 over 30? That's 1. So that's why that just gives me b. Right-hand side, you have to do that in your calculator. And you're going to find that you're going to get around 1.0274. Okay, so that's b. Now, how do we go back and find A? Well, we can just plug it into one of our original equations, right? Let me just choose the first equation. So I have, again, I'll write the variables on the left-hand side. I have A, B to the 10 is equal to 800. So to solve this for A, I'll divide both sides by B to the 10. Right, so the B to the 10s will cancel. And I'm going to get A now is equal to 800 over B to the 10th. But I know what B is. B is 1.0274. So I want to raise that to the 10th power. So that you'd plug into your calculator, and you should get 610.5. You could, since bacteria have to be, an integer number, you could maybe just round that up to like 611 if you wanted. But for now, I'm just going to leave it as 610.5. Okay, so what that means is that my equation now is going to be f of t is equal to 610.5 times b, which we found was 1.0274 raised to the t. So now I have my specific exponential equation. I can answer any questions now, right? And by the way, we already answered question A, because remember question A was, what was the initial size of the culture? That is, so part A, that is what A is, right? The variable A is the initial size, right? It's the initial amount of bacteria. So it's 610.5, or say 611 if you want. If we want to make it an integer number, right? A whole number. Okay, what about question B now? Find the doubling time. Well, there's a couple of ways we could do this, right? We could use the formula that we have now, the specific formula. And then for f of t on the left-hand side, I could set that equal to, I guess it'd be 1221, right? 2 times 610.5. I could double the original amount, set that on the left-hand side, and then solve for t. But that's going to be the same as if we just plug into the formula that we derived earlier, right? Because if you do that, you're going to end up getting the same exact formula. Ultimately, you're going to find that the doubling time t is going to be the natural log of 2 divided by the natural log of b. That will always be the case, okay? So why don't we just plug right into this formula? So I'm going to have natural log of 2 divided by natural log of 1.0274. And if you work that out, it's around 25.64 minutes. And then this has units of minutes. So that would be the time it takes the bacteria to double, right? To go from 610 to double that, which is 1221, I guess, in this case, right? 1221. All right, part C was find the population after 105 minutes. Well, since we know the general exponential function now, go to a new page here. Right, remember, we just found it was f of t equals 610.5. The b was 1.0274 to the t. So if I want to find the bacteria count after 105 minutes, I just plug in 105 for t, right? So really I'm finding f at 105. So this would be 610.5 times 1.0274 to the 105. And if you work that out, you're going to get around 10,431.3. Again, you could round. I'm putting a decimal in there, even though I know you can't have 0.3 of a bacteria. But these are just estimates right now. Okay, and then the last part of the question, so part D, was when will the population reach 11,000? So at what time will the population reach 11,000? Actually, we know just because, by luck, we just got something close to 11,000, a little bit below it. So we know the time's going to be a little bit more than 105 minutes, right? A little bit more than 105 minutes. Well, how do we solve it exactly? Well, again, I start with I'll write this down one more time, with my basic exponential function for this specific problem. And I want to know the time t when the output f is equal to 11,000. So I plug in 11,000 for the left-hand side. And I want to solve that equation for t. Okay, so what's the first step? Well, I better divide both sides by 610.5, right? I need to isolate my exponential term. So I divide both sides by 610.5. So that's gone. Then I have, I'm going to write this on the left-hand side, I have 1.0274 to the t is equal to 11,000 divided by 610.5. And now how do I get that t out? Because I want to solve for t. Here's where you take the log, right, of both sides. So I'll take the natural log of both sides. And then I use that exponential property where the t, the exponent, comes out front. And then all I need to do now to get t is just to divide by natural log of 1.0274, right, both sides. So that will cancel, and in t, if you work that out on your calculator, so here you definitely have to plug this into your calculator, you're going to get around 106.96 minutes. Excellent. That makes perfect sense, right? Because we just said it must be a little bit more than 105 minutes, because in the previous problem we found that the count was 10,433 at 105 minutes, and we want to know when the count was 11,000. So we're getting something greater than 105, and it's only slightly greater, so that seems reasonable. That makes sense. Okay, here's another problem. Actually, I'll do a doubling problem with compound interest. Okay, so this question is asking us to find the time required for an investment to double in value if invested in an account paying 3% compounded quarterly. Okay, so it's a doubling rate question, right? So we need to start with our compound interest formula. So remember, that formula is that A of t is equal to the principal, which we're going to call little a, times 1 plus r over k raised to the k t power, right? So in this case, we don't know the initial amount, but that doesn't matter, so I'll just leave it as a. But we do know that the APR, right, the R is 3%, so that'll be 0.03. And the K, since it's compounded quarterly, remember the K is going to be 4. And then this will be raised to the 4, and we don't know the time. We're trying to figure out the time for it to double, so I'll just leave that as 4t. Okay, let me combine what's inside the parentheses. So if you do this on your calculator, you're going to find that this is equal to 1.0075 raised to the 4t. All right, now what does it mean for the investment to double? Well, if the initial amount was A, then we want the final amount, right, which is capital A, to be twice little a, right? That means we doubled the initial amount, right? Doubled that principal. So I want 2a to equal a times 1.0075 to the 4t. And now I can solve this equation for t, and that'll give me the time it took for a to become twice a, to become 2a. So the nice thing here is, look what's going to happen to the a's. If I divide both sides by a, right, the a's will cancel. Divide both sides by a, so these cancel. And then I just have 1.0075 raised to the 4t is equal to 2. And then how do I find t? Well, I need to take the log of both sides, so I'll take the natural log of both sides. And remember, what that buys us is that I can use that exponential property now. The 4t comes out front. Oops, and I still have natural log of 1.0075. That's going to equal natural log of 2. And now to get t, I can divide both sides by 4 times the natural log of 1.0075. So then these cancel, right? The 4's cancel, and I get t is equal to, you have to do that right-hand side in a calculator, and you're going to get 23.2 years. So that would be the time it takes the value of your account, your initial value, to double, right? Given the fact that it's the interest rate is 3% compounded quarterly. Great. Another application is something called Newton's law of cooling. So let me describe that on the next page. So Newton's law of cooling. So here's what it says. The temperature of an object which I'm going to call capital T, in surrounding air with temperature T sub S, so think of the sub S meaning surrounding air, will behave according to the formula the temperature at some time t is equal to A e to the kt plus the surrounding air temperature. Okay, so let me define what these variables are. So where t, little t, is just the time. So it could be like in minutes, let's say. It could be whatever it is, hours, minutes. So I'll just say time. Little a is a constant determined by the initial temperature of the object. And then K is also a constant And you can think of it as the continuous rate of cooling of the object. So it's a continuous rate of cooling. Okay, so actually let's do a problem that involves Newton's law of cooling. I'll start a new page for this. Okay, so this question says a turkey is pulled from the oven when the internal temperature is 165 degrees Fahrenheit and is allowed to cool in a 75 degree room, right? 75 degree Fahrenheit room. If the temperature of the turkey is 145 degrees after half an hour, so 30 minutes, right? We're going to use our time in minutes. So 145 degrees after half an hour, what will the temperature be after 50 minutes? And then how long will it take the turkey to cool to 110 degrees? Okay, so to start, let me write down the basic Newton's law of cooling formula, right? We know that the temperature at some time t is equal to A e to the kt plus T sub s, right? That was the initial function for Newton's law of cooling. What do we know? We know that T sub s is the surrounding room temperature, so that's going to be 75 degrees, right? 75 degrees Fahrenheit. We also know the temperature when the initial temperature, right, when T is 0, is equal to 165 degrees Fahrenheit. So actually, we can use that information to solve for A. Because ultimately, right, we want to find A and we want to find K. So we can use that initial information to find A. So let's plug it in. So we have the temperature at 0 time is 165. So that's the left-hand side. That's going to equal A times E to the K, but the time is 0, right? We're saying at 0 time, it's 165 degrees, so the time is 0. And I also know that TS is 75. Okay, why does this help? Because remember, first of all, what's K times 0? K times 0 is 0. And then what is E to the 0? Well, anything to the 0 power is equal to 1, right? So this is just saying 165 is equal to A plus 75. So I can solve that for A, right? If I subtract 75 from both sides, then I'm going to have A is equal to, I guess it would be 90 in this case. So A is 90. Okay, so now I have, I'm going to write the whole Newton's law of cooling equation out again, but I'm going to plug in for A. I know A is 90, E to the kt, and I also know that the surrounding room temperature is 75. Okay. So now I want to use the second piece of information to find K. Well, what do I know? I know that the temperature is 145 degrees after half an hour. So the temperature, right, the left-hand side is 145 when the time, little t, is a half hour, but we're going to write it in minutes. So this will be 30 minutes. Okay, so I need to solve that equation for K. So I need to isolate the exponential. So first, let me subtract 75 from both sides. So I'm going to get 70 is equal to 90 E, and I'll write this as 30K. So now I need to divide both sides by 90. Right, so these cancel. So now I have E to the 30K is equal to 70 over 90, which I can write as 7/9. And then I could take the log, remember I want to get K, right? So I could take the log of both sides. So I'll take the natural log of both sides. let me finish the problem over here. So remember our rule, the exponent can come out front of the log. So this is really just 30k times natural log of e is equal to natural log of 7/9. But what's natural log of e? Remember, that's log base e of e. That's just equal to 1, right? Natural log of e is equal to 1. So this is saying 30k is equal to natural log of 7/9. Now if I divide both sides by 30, I'll have my k. So k equals, you do that in a calculator, and you're going to find it's around negative 0.008377. Okay, great. So we have k now. Good. So now let me plug everything that I have in now. So I know a, I know k, I know t sub s, right? So let me go another page. So remember, the original equation was the temperature at time t is equal to a e to the kt plus t sub s. But now I have all the information I need, right? So the temperature at time t is going to be a. Well, we found a to be 90. We found k to be negative 0.008377. I have to multiply by t plus, and then the room temperature was 75. Okay, so now we can answer question A, right? It said, what will the temperature be after 50 minutes? Well, to answer that question, I just need to solve for the temperature when little t is equal to 50, right? So I want to evaluate capital T at 50. So what does that mean in terms of the equation? Just plug in 50 where I have a t. So this time up here is going to be 50. So this you have to work out on your calculator, right? And if you work this out, you're going to find that this is equal to 134.2 degrees Fahrenheit. All right, so that's the temperature when the time is 50 minutes. And then the second question, part B, so that was really part A, right? Part B was to find the time, right? How long will it take the turkey to cool to 110 degrees? So now I want my temperature, my left-hand side, to be 110. And I want to solve this equation now for t, right? Little t, the time. I don't know the little time here. Okay, so how do we solve this for little t? Well, I need to first subtract 75 from both sides, right? Get rid of that 75. So 110 minus 75 is going to be 35. So I have 35 is equal to 90 e to the minus 0.008377 t. Now I need to divide both sides by 90. So I'm gonna write the right hand side and the left hand side, just so I have my variable on the left hand side. So the 0.008377 t is equal to 35 over 90. I can simplify that a little bit, right? I guess, let's see, 5 goes into both, right? So I could write this as 7. 35 divided by 5 is 7, and 90 divided by 5 is going to be 18, so 7/18. And then how do I get the t? How do I solve for t? I need to get the exponent out front, so I need to take the natural log of both sides. So now I can use that exponential property, right? This will come out front. So 0.08377t times natural log of e equals natural log of 7/18. But natural log of e is just 1, right? So now all I have to do to get t is divide both sides by that really small number there. Right, so if I divide both sides by negative 0.008377, that'll cancel and I'll get t equals, so this you have to do in your calculator again, and if you work this out, you're going to get around 112.74 minutes. So we're saying that the turkey is going to cool to 110 degrees in about 112.74 minutes. Great. So again, it was just an application of exponentials and logarithms. Okay, I want to do one more application, and this is on like the Richter scale, or it's actually called the moment magnitude scale. It's like formerly, it kind of replaced the Richter scale for earthquakes. So let's do one more problem. Okay, so again, this is called the moment magnitude scale. And basically, it replaced what you might be more familiar with called the Richter scale for earthquakes. I don't know the details of if it's more accurate or why it replaced it, but it replaced the Richter scale. Okay, so here's what this moment magnitude scale is. For an earthquake, with seismic moment S, which is a measurement of Earth movement, so S is a measurement of Earth movement, or you can also think of it as the intensity. Then the MMS value, so the moment magnitude scale value, so MMS is just moment magnitude scale value, or magnitude of the earthquake, is given by this function. It's M, so that's going to be the magnitude, right, of the earthquake. That's the MMS value. That's equal to, I'm just calling it M now, it's 2/3 log of S, remember that's the measure of the intensity, the seismic moment, divided by S sub 0. Where S sub 0 is just like a baseline measure, and it has a value. So where S sub 0 is equal to 10 to the 16th, so it's 1 with 16 zeros after it, so it's a very large number, is a baseline measure for the seismic movement. Okay, so let's do one problem with this particular example. Okay, so the question is, the 1906 San Francisco earthquake had a magnitude of 7.9 on the MMS scale. Later, there was an earthquake with a magnitude of 4.7 that caused only minor damage. And the question is, how many times more intense was the San Francisco earthquake, was the first San Francisco earthquake compared to the second one? So really, ultimately, what we want to do is we want to compare the seismic moments, right? The intensity, the S's. So the goal here is we want to compare the seismic moments Remember, that's a measure of the Earth movement or the intensity. So I want to compare the S's. All right, so the way to do this is to solve both equations, right? Solve both earthquakes for the S values, and then we can just form a ratio, and that will give us the comparison, right? So we know that the general formula for the magnitude, right, the MMS value, M, is equal to 2/3 log base 10 of S over S naught. And we know that S naught is 10 to the 16th, right? Okay, so let's plug in what we know. Well, in the first earthquake, so this is like the first earthquake, and then I'll do, in parallel, I'll do the second one over here. So in the first earthquake, the magnitude was 7.9, right? And that's equal to 2/3 log of S over S naught. In the second earthquake, the magnitude was 4.7, and that's equal to 2/3 log of S over S naught. All right, let me call this S S1 and this one S2, meaning the seismic moment for the first earthquake, and S2 is the seismic moment for the second earthquake. So I want to solve for S1 and S2. Well, how do I do that? I need to rearrange this equation, right? I need to solve for S1. So first thing I would do is probably multiply both sides by 3/2 to get, or you could divide by 2/3, right? Same thing. So I'll just multiply by the reciprocal by 3/2. Why? Because I want to get rid of this 2/3 here. S1 over S naught. And then same thing over here. So I would multiply by 3/2 times 4.7. And that's 3/2 times 2/3 times log of S2 over S naught. Okay, now let me put the log term on the left-hand side now. So the reason why I did that is this will cancel, right? And then same thing over here. So I get the log by itself, but I'm going to write it on the left-hand side. So log of S1 over S naught. That's equal to, and then 3/2 times 7.9 is 11.85. And on this side, I'm going to get log of S2 over S naught. And that's equal to, well, 3/2 times 4.7 is 7.05. Okay, now remember, how do we solve log equations? We isolate the log, which we did, and now we're going to exponentiate both sides, right? And since this is log base 10, 10 is going to be the base. So in other words, I want to do 10 raised to the log of S1 over S naught, and the other side is going to be 10 raised to the 11.85. And over here, it'll be 10 raised to the log of S2 over S naught, and the right-hand side will be 10 raised to the 7.05. Okay? Why do we do that? Because remember, those are inverse functions, right? Log base 10 and 10 to the x. So 10 raised to the log of s1 over s naught is just s1 over s naught, right? It gives back s1 over s naught. And that's equal to 10 to the 11.85. You could work that out, but I'll just leave it with the exponent for now. And then the right-hand side is going to be s2 over s naught is equal to 10 to the 7.05. Okay, so what this is saying is, for the first earthquake, if I multiply both sides by s naught, I have s1 is equal to 10 to the 11.85 times s naught. Again, you could plug in your 10 to the 16th, but you don't need to do that. I'll just leave it as s naught. And then for the right hand, the second earthquake, I have s2 is equal to 10 to the 7.05 times s naught. Now, I want to compare the strengths of these two earthquakes, right? I want to compare the s's. I want to compare s1 to s2. So how can I do that? The easiest way to do this is just to form the ratio, right? So if I do s1 divided by s2, that'll tell me how many more times s1 is compared to s2, right? So how much stronger s1 is. Well, s1, remember, is 10 to the 11.85 times s naught over, and then s2 was 10 to the 7.05 times s naught. So you could have plugged in s naught, but you don't need to, because look what happens to the s naughts. They cancel. So the ratio s1 to s2 is simply equal to 10 to the 11.85 divided by 10 to the 7.05. Well, do you remember how to simplify if you have a power divided by a power with the same base? Remember, the rule is you keep the base and you subtract the exponent. So this would be 11.85 minus 7.05. And that's just going to be 10 to the 4.8. Right, when you subtract those. But what is 10 to the 4.8? So now you can do that in your calculator, and it's around 63,096. So 63,096. So what we're saying now, actually, if you want, you can multiply both sides by S2. So I could say S1 is equal to 63096 S2. So what that's saying is that S1, earthquake 1, is 63,096 times as strong. Right? So it's 63,096 times as strong as S2. So even though the moment magnitude scale only went from 4.7 to 7.9, since it's a logarithmic scale, the 7.9 is much more intense than the 4.7. It's 63,000 times as strong. All right, great. So that's it for section 4.6. In fact, that's it for chapter 4. So next what I'll do is I will start talking about chapter 5, and we're going to do certain sections of chapter 5 where we look at trigonometry. So trigonometric functions. We'll talk about right triangle trig, trig functions in general, and then we might even do a little bit with the vectors. We'll see how much time we have, if we can get into vectors at all. Great, thanks.